So we're going to talk about arithmetic and geometric sequences today. Have you guys ever heard those phrases? Arithmetic or geometric sequences. If you have, it was in Math 1, because there is a little bit of this there in Math 1. I haven't taught Math 1 in about 3 years. I used to I did it, but we skimmed over it. We barely looked at it. So you may or may not have really seen much of this at all. Here, so a sequence. Is a function from the whole numbers to the real numbers. Okay, this means that we can only plug whole numbers, 0, 1, 2, 3, etc., into a sequence. But we can get any real number out as the output. So whenever we do functions, we don't limit what can be plugged in. For functions, we can plug in 1.2. We can plug in 3.7. We can plug in the square root of 22, right? For sequences, only whole numbers can be plugged into the sequence. Thus, a graph of a sequence will only be points. Because you won't have values in between there, because you're only plugging in 1, and then 2, and then 3. So you're just going to have like a graph with points on it. However, they're going to behave a lot like functions. They're just not connected there. So you have been doing sequences since you were little, right? Henry comes home sometimes with homework in like 1st, 2nd, 3rd grade with sequence problems. You just may or may not have called them sequences, right? They're just patterns. So like if I have -3, -2, 1, 4, what's the next number going to be? 7. Then 10, and then 13, right? My sequence is just that I'm adding 3 each time. How about this next one? 3, 6, 12. 24, then 48, then 96, right? So what is our rule in this sequence? You're doubling the number, right? The next couple are a little bit trickier. Henry wouldn't see these two on his homework yet. So 8.25, 8.9, 9.55. I gotta double check you because my mental math is failing me right now. I think you're right. Yep. Oh no, nope. You're off just a little bit. No. 30. 10.3. Because what you're doing here is you're adding 0.65. Right. Now, that one's a little tougher to just see. I grabbed the calculator for that one. If you want to see what's happening here, you can just take any term, like 8.9, and subtract 8.25. And that is going to give you 0.65. And then you can check and see 8.9 plus 0.65 is going to give you 9.55. So this gives you 10.3. Next would be 10.95 and then 11.6. Okay, what about this last one? What's happening here? Multiplying by -2. So our next one is going to be positive 16, then -32, and then positive 64. All right. So whenever we're multiplying by a negative number, what do you notice about the outputs of the sequence? They're switching back and forth from positive to negative. So if you ever see that happening, if you see values go positive, negative, positive, negative, positive, negative, you are probably multiplying by a negative in that case. All right, so we have to learn some notation for this. So let me get this. All right, so we have to use recursive notation for some of these. And when you're dealing with a sequence, typically they will use n's sort of as the variable instead of x's. And so if you have a term, it is called like the a sub n term. It's the output whenever you plug in n. A sub 0 is the initial value because it's the output you get when you plug in 0, which is the first number that you can plug in for a sequence. N is the number that is entered into the sequence. So there are a couple ways that sequences can be defined. Both of these for 5 and 6 are explicitly defined. Okay, so these are explicitly defined, which means they have an n in their equation, right? These work just like functions. It's just the notation looks a little bit different. So if we have ones that are explicitly defined, and I'm going to do a little bit that are not. I think I got it in here. But best I can tell, the AP exam is only going to give you explicitly defined functions. Although I'm a little afraid something else is going to show up, so I'm going to show you a little bit of the recursive. So whenever you see an n right here, if you're asked for a sub 4, all you do, you're going to say a sub 4. That's a lot like saying f of 4. You're plugging 4 in, and you're just replacing that n with 4. So 3 times 4 minus 5, which is going to give you 12 minus 5, which is 7. There. So it's really a lot like function notation. It's just a different way of writing this here. A sub n, I'm sorry, not n in that case. A sub 2 for this next one, we would do 2 times 3 to the second power. And what do I need to do first when I am solving this? Exponents have to come first. So I'm doing 2 times 9, which will give me 18. So really just a lot like functions, just different notation there. Okay, now, we also can have functions that are recursively defined. If functions are recursively defined, they don't have just an n in the function. Okay, so if you look at the equation right here, I see a sub n, and I see this a sub n minus 1. So they didn't just put just an n in there, right? Whenever we see a sub n, we know this is the nth term. A sub n minus 1 is the previous term. Now, when you see these, you cannot just, well, you could just plug in a 3. It will not get you anywhere. You won't know what to do, right? So, in this case, I need to know a sub 3. But if I try to plug in, if I try to do a sub 3 right now, I'll get 2a sub 3 minus 1, which is 2a sub 2. I don't know what's in those crazy lines for me there. Do I know what a sub 2 is? I do not. So whenever you have a function that's recursively defined, where you have that a sub n minus 1, what you're going to have to do instead is you can't go from a sub 0 to a sub 3. You have to find all of the ones in between, right? So this tells me that a sub 0 is 5. So what I need to do is I need to find a sub 1. Okay? So a sub 1 would equal 2 times a sub 1 minus 1. Right? What's 1 minus 1? 0, right? So we got a sub 0. Do they give us a sub 0? Right, here it is. It equals 5. So a sub 1 equals 2 times 5, which is 10. Then I need to use that to find a sub 2. Right? So I'll have 2 times a sub 2 minus 1, which is 2 times a sub 1. You'll see sort of the pattern happening here. A sub 1 is just the one we got before, right? So a sub 2 is 2 times 10, which is 20. And then I'd really already started a sub 3 over there. A sub 3 would be 2 a sub 3 minus 1. That's a sub 3 equals 2 a sub 2. A sub 2 was the last one we just found, which gives me 2 times 20, so I get 40 for my answer. Now, you don't necessarily have to show all of that work. You could just look at the pattern that's happening. Like if I were doing this problem, here is probably what I would write down. I'm going to use a different color just to show you how you could shortcut this a little bit. I would probably say, I already know a sub 0 is 5. A sub 1 is 2 times the previous term. A sub n minus 1 is the previous term, right? So that's 2 times 5, which will give me 10. And then a sub 2 would be 2 times 10, which will give me 20. And then a sub 3 would be 2 times 20, which will give me 40. So I wouldn't necessarily write every step of that down for the problem. So if we look at example 8, I can see that I have a recursively defined function here, and I've got a sub n, which is the nth term, equals a sub n minus 1 minus 4. So that's the previous term. So when you see that a sub n minus 1, that's the previous term. So if I've got a sub 0 equals negative 2, then I can't go straight to a sub 4 because this is recursively defined. I don't have just the n to plug in. So I have to go a sub 1. And a sub 1 means I take the previous term and I subtract 4. So I'll have negative 2 minus 4, which will give me negative 6. And then I need to find a sub 2, which will be previous term, negative 6, minus 4, which gives me negative 10. Right? So we're subtracting 4 each time. A sub 3 would be previous term, which is negative 10, minus 4, which gives me negative 14, and a sub 4 is negative 14 minus 4, which gives me negative 18, and that will be my final answer. Okay, everybody okay with that notation? All right. So there's lots of types of sequences. Not all sequences are arithmetic or geometric, but arithmetic and geometric sequences are special types that we like to look at. So arithmetic sequences are formed by adding a constant value to each successive term. Sometimes it looks like you're subtracting, like on that last problem that we did, but you could also think of that as adding -4. So sometimes it looks like subtracting. That constant value is called the common why has it left me? Geometric is common ratio. Common difference. That's it. Arithmetic sequences behave like linear functions, except they are not continuous. Right? So rather than having a straight line, we just have a bunch of dots that are in a straight line. Okay? Arithmetic sequences have a constant rate of change. So, if I have an arithmetic sequence such as a sub n equals 1/2 n minus 3, this function is defined explicitly because it just has an n, right? So it's not a recursive formula where we've got like the a sub n minus 1. It's defined explicitly. This acts just like the line y equals 1/2 x minus 3. The only difference is that we can only plug in whole numbers. So like if I plug in 0, I will get -3. So I'll have the point at 0, -3. If I plug in 1, I get 1/2 minus 3, which will give me -2.5. So I've got the point 1, -2.5. If I plug in 2, 1/2 times 2 is 1. Subtract 2, I'll get -2. You can kind of, here, instead of plugging in numbers now, start to see your pattern, right? Because I see that, like, oh, this is just going down 0.5. I'm sorry, it's actually up because these are negative numbers. This is up 0.5. So you could just continue with that pattern, right? So -1.5, -1, -0.5. So if we graph all of these here, I've got the 0.3, -1.5, 4, -1, and 5, -0.5. Now, we don't fill in with a line on this one because for a sequence, it's just going to be the ones where you plug in those whole numbers. But we can still think of it like our y-intercept is -3. Our slope is 1/2. We're just not connecting the dots. Okay. Sometimes you will be asked to find the common difference for sequences. To find a common difference, you are finding the number that is being added or subtracted each time. If I look at the second one, they didn't ask for common difference here. That one's really easy to see. What's your common difference, for example, 11? It's 2. You can tell very easily what the common difference is there because it's nice, easy, whole numbers. Little tougher here, but an option is always take any term, so like -3.1, and subtract the term that comes before it, right? So if I do -3.1 minus -5.5, I will get +2.4. And then check to make sure that's right. So like if I take -3.1 and add 2.4, I get -0.7. If I add 2.4 again, I get 1.7. So the common difference here, a lot of times we'll just use a D for that, is 2.4. Now, it doesn't matter which terms you pick. Like, I could have done 1.7 minus -0.7. In fact, if I was doing this on the calculator inactive section, that would be a little bit easier because this turns to adding right here, and I would just have 24, carry that to get a, I'm sorry, carry the 1, and get 2.4 for that. So it doesn't have to be any specific term. You just take any term and subtract the 1 before it. Okay? For the example 11, I've got 6, 8, 10, 12, 14. I can see that my common difference here is going to be 2, right? So that is a number that's being added each time. So when we want to write that as an equation, if we want to write that as an explicit equation, right, I want a sub n equals, and then I want to have, you know, a formula here for this. I don't love whenever they give us like 6, 8, 10, 12, 14 and don't specify whether this is a sub 0 or a sub 1. However, usually it's going to be like multiple choice where there's like both options are not there, right? Let me remind myself what I put right here to... We're going to treat it like a sub 0. There. So if you think about like what's happening here, this first term is like my n is 0, my a sub n is 6 right here. So that is your y-intercept. That's where you cross the y-axis, right? And since this is arithmetic, we know it's going to look like a linear equation. So we're going to say a sub n equals, the common difference is the slope. Oh, excuse me. So we could have like 2n plus 6. And if you want to test it to make sure it works, if I do a sub 0, I'd have 2 times 0 plus 6, and that would just give me 6. And if I do the next term, I'd have 2 times 1 plus 6, and that would give me 8. And if I do the next term, I do 2 times 2 plus 6, which will give me 10. And you can see I'm getting the numbers in order here. So, here, let me do this. Come on. In that box down there at the bottom, the arithmetic sequence can always be written as a sub n equals a sub 0 plus d, which is our common difference, times n. You may even want to write out over here to the side that a sub 0 is like your y-intercept, and d, or your common difference, is your slope. Okay, questions? All right, so here we have an example where we got the third term of an arithmetic sequence is 9. The fourth term is 13. What is the value of the 10th term? Okay, so we know that this is an arithmetic sequence. We know that we're adding a number each time, right? They tell us third term, a sub 3, is 9. And the fourth term, a sub 4, is 13. Okay. What would the common difference be here? Plus 4, right? To get from, like, thankfully they gave us two that are right next to each other, so we can just pretty easily see that you add 4. They don't have to do that, but a lot of times they will, right? So my common difference is 4. So if I want to know the 10th term, one option is to just do a sub 5 equals, we're going to add 4, 17. A sub 6, add 4 more, 21. A sub 7, add 4 more, 25. A sub 8, add 4 more, we get 29. A sub 9, add 4 more, we get 33. And a sub 10, add 4 more, we get 37. And that'll be our answer. All right. If they give you fairly low number terms, I think that this is just the easiest, like, foolproof way to do it because you can still do it pretty quickly. However, sometimes they might ask you for, like, the 45th term or something like that, in which case trying to do something like this is going to be a pain, right? So it would be nice if we sort of have a shortcut that we could think of here, right? So let's think about it. I knew that a sub 4 was 13, and I was trying to find a sub 10. Okay, so if I want to start from 13, or you could start from 9, either one, right? How many times was I going to have to add 4? Okay, how did you know it was 6? Okay, so I was going to have to add 4, 10 minus 4 times, right? Because I have the 4th term. I'm looking for the 10th term. That's 6 terms I've got to find. So I'd have 13 plus 4 times 6, which would be 13 plus 24, which gives us 37. Now, if I didn't, but if I asked you for something like a sub 45, right? Going all the way out to the 45th term would take forever. So, to find the 45th term, I could take the one I know, 13, and I know I'm going to have to add 4, 45 minus 4 times, right? And so I could do 13 plus 4 times 41, which would be 13 plus 164, which would give me 177 for that. Definitely, the shortcut is better if you've got to go way up high, because writing that out that many times would take a very long time to do, and you're likely to make a mistake somewhere when you're out that many. If we want to sort of make this shortcut a rule, into a rule, let me send that to the back so it shows up. We could make our rule where a sub n equals a sub k here, and this a sub k, in this particular case, it was my a sub 4. It was the known term, right? So this right here is your known term. And then you've got your common difference or the number that you're adding each time times whatever number you're looking for minus whatever term that was, like it was a 4th term in this particular case. So this rule will work every time. It'll be a nice shortcut for when you're asked to find terms that are really high. Okay, questions here? All right, let's keep going. Let's talk about some geometric sequences. Geometric sequences are formed by multiplying. A constant value by each successive term. The constant value that's being multiplied is called the common ratio. And geometric sequences behave like exponential functions. Except for, much like the lines, they're not continuous. It's just going to be a bunch of dots that increase or decrease exponential. Geometric sequences have an either increasing or decreasing rate of change. All right, so, for example, here is an exponential equation. In an exponential equation, or at least the type that we're going to look at, you're going to have a number times another number being raised to a power with a variable there. So, if I plug in 0, I would have 80 times 80 times 1/2 to the 0 power. What is 1/2 to the 0 power? It's 1. Anything to the 0 power is 1, so I'm going to get 80 here. If I do to the first power, 80 times 1/2 to the first power, that's going to be half of 80, which is 40. If I do 80 times 1/2 to the second power, when you square a fraction, you just square the top, square the bottom. So that's going to be 80 times 1/4, and a fourth of 80 would be 20. Now, what does it look like we're doing each time as we go down to the next line? Just divide by 2. So you could just start using the pattern here. 10, 5, 2.5. And multiplying by 1/2 is the same as dividing by 2. So this makes sense for this problem, right? So if we graph it, this is what it would look like. I've got 0, 80, 1, 40, 2, 20, 3, 10, 4, 5, and then 5, 2.5. We don't connect anything because this is a sequence, so it's only the dots. And typically when we think of exponentials, we generally think about like things that are increasing really rapidly. But in this case, we have exponential decay, which is also a very common occurrence. There are lots of things that behave in this way, and as we get into exponentials more, we'll talk about some of those applications. Right. All right. So, whenever we look at a sequence and they just give us the numbers, there can be some pretty like telltale signs that we're dealing with a geometric sequence instead of a arithmetic. So if you see decimals that keep getting worse and worse, almost always going to be geometric sequence. They also ask you for the common ratio, which tells you this one is geometric, right? If you see numbers that are getting larger really quickly, also indicates geometric sequence for that. So if I look at this problem, I've got 100, 102, 104.04, 106.1208. So if this is asking for a common ratio, that means I'm multiplying by some number. Not immediately clear what number that is, but if I look like at 15, what number are you multiplying by for number 15? You're multiplying by 3. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54, right? So sometimes it's very easy to see the common ratio. Other times it's not. So very much like we did with the common difference, if you need to know the common ratio, you can take any term. So like I'm going to use 102 and divide by the term that comes before it. And 102 divided by 100 is going to be 1.02. So my common ratio, I'm going to use an R right here, is 1.02. And then you can check that by multiplying. If you do 1.02 times 102, you will get 104.04 there. I don't necessarily have to use 102 and 100. I could do 106.1208 and divide it by 104.04. However, this one's obviously a little easier to deal with for that. It's less necessary to do this for number 15, but it would work if I do 6 and divide by the term that comes before it, I get 3. Or if I were to do 54 divided by 18, I would get 3. So, I think these are a little harder to think about. This box right here, that's here, it was supposed to be covering up the answer to this. That was supposed to be filled in here. That's a mistake. I forgot to move it back. There, so there's not any reason for this box being here. So if we're writing an equation for this sequence, I need something where I can do a sub n equals, and then I can plug something in here. I want you guys to try that on your own. So you're looking for an equation like, let me give you one that does not work, so you got an idea of what I'm looking for. Like I know these are supposed to be like exponential, so I'm going to give you one that doesn't work. Like a sub n equals 2 times 6 to the n power, right? That one is not going to work. If I plug in 0, I'll get 2 times 6 to the 0 power, which will be 2. That actually works, but if I plug in 1, I've got 2 times 6 to the first power, which is 12. And what is the next one I'm supposed to get after 2? Supposed to get 6, not 12, right? So this would not work. So you guys look at it and try to come up with an equation that would give me the terms that I'm looking for as I plug them in. Check with your neighbor and see if they've got anything. See what they're thinking. I've see a few of you. I know I've seen at least one right one, but I see a lot of you just blank. So talk to your neighbors, see what they think. All right, who has one that they think will work here? What you got, Will? You got anything else with it? To the nth power, yes. So if I plug these in, if I do a sub 0, 2 times 3 to the 0 power, 3 to the 0 power is just 1, so that's 2. If I do a sub 1, 2 times 3 to the first power would be 6. That's the next number I'm supposed to get. If I do a sub 2, I would have 2 times 3 to the second power. You got to square that 3 first, which is 9. Multiply that by 2, which gives you 18. Beautiful. This is it for that one. Okay, now, we should be noticing something here, that our initial term, our a sub 0, was this term right here. And our common difference, the number that we were multiplying by, that went right here, right? And actually, a lot of the stuff that Mr. Passwater uses, when he has a geometric sequence, he'll use a G sub n. That is not anything like that has to be done. A is a very typical letter to be used. G will be used sometimes. They don't necessarily have to use A or G. They could call it like M sub n or T sub n or something like that. So it could be any letter. But Mr. Passwater in his notes uses G sub n when it's geometric rather than an A sub n. So if I wanted to change that to a G right there, I could. That's not something that you have to do, but you could if you wanted. So when we write a geometric sequence, we can always write that sequence as G sub 0, whatever my initial term is, times the common ratio to that n power right there for that. So if we have something like 16, where we are looking for the fifth term of a geometric sequence is 12, and the fourth term is 6. So I'm going to use a G like Mr. Passwater does, but you could use an A here if you want. G sub 5 is 12. G sub 4 is 6. And they're asking us for G sub 10. So they do a couple things here that you got to be careful of. They give you the fifth term and then the fourth term. But really we want to be thinking about these more in order, right? Like G sub 4 is 6 and G sub 5 is 12. What is your common ratio here? What number are you multiplying by? 2, right? So we are multiplying times 2. So you have the option of just doing G sub 6 equals 24. G sub 7 is going to be 48. G sub 8 is going to be 96. We might be getting out of my ability to do this pretty soon. Let's see, 90 times 90 is 180 plus, is it 192, I think? Yep. And then G sub 10, we got to double that. Oh, good gracious. What? 384. Sounds right for that. So, this is an option. If they have given you small numbers, it's a good way to do the problem. If this is, I would feel a little worried about this if it wasn't calculator active. A lot of times the geometric, they have to either give you small numbers or make it calculator active, because things get out of hand quickly with geometric sequences, right? The numbers start to get really big quickly. But sometimes you got to find a much bigger number. So if you did, you wouldn't want to just do this. You would want some sort of shortcut. So let's think about what we could have done instead. So if I'm looking for G sub 10, right? And I could pick G sub 4 or G sub 5, but G sub 5 is the highest one. I know I've got 12, right? I'm starting off with 12. And then I'm having to multiply 12 by 2, right? So I'm going to have to do 12 times my 2. How many times did I have to multiply by 2? It'd be 5. And how do we know it's 5? We start on the 5th, right? And we want to get to 10. So if I do 10 minus 5, then I've got 12 times 2 to the 5th. 2 to the 5th is 2 times 2 times 2 times 2 times 2, which is going to be 32. So I'm doing 12 times 32. And then 32 times 12, 4, 6, and then 32. Add those together, and we get our 384 that way as well. So you've got the option of just like writing out each term, or you could shortcut it by thinking, oh, here's where I'm starting. I need to multiply by my common difference how many times, right? So, let's see here. Send that back. Let me do that. So, another option for this, the shortcuts or the formula for the shortcut here, is when you write when you're looking for G sub whatever number, right, you can take your G sub K, which is your known term, right? This is a known term. And then you multiply by your common ratio, which is the set number that you're multiplying by there, and raise that to the difference between the term you know and the term that you're looking for there. All right, questions? All right, so here are some examples of some things you might see. Consecutive terms of a sequence have the values of 10, -5, 5 halves, and -5 fourths. Of the following, which describes the sequence? Okay. So you can see all of your options, except for the last one, say this is a geometric sequence. The last one says this is not a geometric sequence for a weird reason. I'm feeling like it's not D, but we'll see. So if we are going from 10 to -5, what number are we multiplying by? It's going to be -1/2. You also are dividing by -2, but the ratio always has to be the number that you are multiplying by. All right, so if you're dividing by a number, then it's really 1 over that number is your common ratio. So for B, I would multiply by -1/2 each time, right? So I can tell that it's going to be a negative because of the switching from the positive, negative for that. Okay, here I have a consecutive terms of a sequence, 8, 5, 2, -1. Which one could be the case? Now, this time I've got both arithmetic and geometric options. Which one am I dealing with here? Geometric or arithmetic? Arithmetic. here because you are just adding or subtracting. So B and D are out. And so my options, I've got, now I can throw one of these out without even thinking about the number. Okay? I've got an arithmetic sequence with a common difference of -3 and an arithmetic sequence with a common ratio of -3. Which one of those has to be right? The difference, because arithmetic sequences don't have common ratios, right? They almost threw like a vocabulary question in there because the numbers they gave you are all the same. This is making sure that you know that that number you're subtracting by is the common difference. Okay? The general term of a sequence is given by a sub n equals 25 plus 2 times n minus 5, where a sub 0 is the initial value. Which of the following expressions also gives the general term of the sequence here? Any ideas? This particular problem is an arithmetic sequence, but it looks complicated, right? It doesn't look like a line. It doesn't look like y equals mx plus b. But the only thing you have to do here to get this in a like y equals mx plus b sort of form is distribute that 2. So a sub n would equal 25 plus 2n minus 10. And then combine your like terms. So they write the number first at 25 and -10 is going to give you 15 plus 2n, which is going to be b. So you're just simplifying to see which one matches there. All right, I don't like these problems. I think they are confusing, but I'm afraid that you may see one. I am not going to put these on your test because I think they are confusing. If I give you a problem like this, and I may, I'll add one more thing in that I think helps a lot. 20 says the first term of an arithmetic sequence is 6, and the common difference is 3. What is the 7th term of the sequence? Sounds like a pretty simple problem, but what makes students miss this one so much is their interpretation of first term, right? First term is a sub 1. A sub 0 is called the initial term. And to me, it's understandable why those are easy to get mixed up, right? Because something that's first also sounds like it's initial, right? So it's easy to get those mixed up. So what I'll do, if I give you a problem like this, I will, in parentheses, I'll say something like a sub 1 equals 6, right there for that first one. So it's very clear that this is a sub 1 and not a sub 0, right? So our common difference is 3. What are we doing? Multiplying by 3 or adding 3? Adding 3. Which 2 do you think we can probably throw out? C and D looks like they probably had you multiplying there, right? If a sub 1 is 6, you can just say, well, a sub 2 is going to be 9, and a sub 3 is going to be 12, and a sub 4 is going to be 15. A sub 5 is going to be 18, and let's see, we got to go 7. A sub 6 is 21. A sub 7 is 24. And that'll be your answer. However, if you let a sub 0 equal 6, you're going to get 27 for this, so I find it a little difficult. You could shortcut it, right? If you want to know a sub 7, you could start with the term you know, which is 6, and then you've got to add 3 And you got to think about how many times 7 minus 1, because you're starting at the first term and you're trying to get to the 7th term. So 6 plus 3 times 6 is 6 plus 18, which also gives you 24. All right, so you've got options on how you want to deal with that. Questions? Okay, so we got through everything there, which is good because those notes are a little bit long.